This is Computing Up, conversations about computation writ large with Michael Littman and Dave Ackley. This episode was recorded August 18th, 2022.
Hello and good afternoon. Dave, how you doing?
I'm doing all right. How are you doing?
I'm
So
great.
So you are getting over COVID.
I had a visit from the COVID fairy. Actually, I brought back European COVID because it's kind of fancier.
Sure. I hear it's big in Europe.
Yeah, I went to the IJCAI conference in Vienna, Austria, which was very cool, except that I came back with COVID. And it's been unpleasant for coming on to 3 weeks now. I don't think I bounced back like a lot of people are saying that they're bouncing back.
So how do you feel about like brain fog and all that sort of thing?
I have some brain fog, definite words out mouth, like troubles. I've been noticing that, like I just talking to my wife and I just stopped talking at some point and I'm like, I need to work on this sentence a little bit. I'll be right back.
Yeah, let me get back to you.
It's not good.
Wow.
It's not good. And things taste really, really salty.
Oh, you were saying everything tasted like a big pretzel.
Like I just had a big soft pretzel and with the big chunks of salt on them, like you get in Philadelphia.
Wow. That's pretty weird. This goes to the nature of reality, though.
Yes. This has definitely interfered with reality for me. But I noticed that your Twitter little image took its mask off.
Yeah, I did.
Does that mean you're less concerned about Twitter now? Getting bad things from Twitter?
Well, for your Twitter's going to get to you without a mask or not. But I don't know. I mean, we haven't changed our behavior. We're still locked down. We're still getting grocery deliveries. We're doing everything. We haven't gotten COVID in our bubble yet. It just felt like it was time for a change. And, I had this cool hat, so I put a picture up. That's
all right. Well, I hope you stay healthy. I definitely would not recommend, like when my wife got it and then she got over it really quickly and I stayed away from her. So I didn't get it from her. She also got it from Europe, from Iceland. And I thought, well, great. So, first of all, I'm obviously immune if I didn't get it from her. And second of all,
Right.
She bounced back really well. So I wish I had just gotten it with her, it would have been fine. But then when I actually got it, I would not recommend it.
Yeah, you got
I'm
kicked.
sorry. I got a little kicked.
So are you not going into work at this point, or you weren't going into work anyway?
It's all complicated. Work is complicated. Right now, I'm actually in Rhode Island and I'm working in Virginia, so that's definitely not going in.
There's a commute.
I did go to the White House, though, while I was,
Wow.
I'm going to say not sick. According to the CDC guidelines, it was okay for me to be out.
Wow. No, that's exciting.
Yeah, it was, not technically the white part of the White House. It was the Eisenhower Executive Office building, but I now have like business there because that's what happens when you're a government person.
Wow. Well, yeah. I'm impressed down here.
Well, cool. So nonetheless, in spite of all these goings on, we lined up a really fun guest for today, and that is Peter Norvig, who's joining us from the West Coast. Peter, how are you doing?
Good. How are you?
I am, as you know, quite well.
Yes. Yeah.
Considering.
But I've been really wanting to have a chat with you in this forum for a while now. You're just you've done so many cool, interesting things over the years, and you're such a character. And I just thought it would be really fun to kind of pick your brain a little bit and see what's on your mind. So why don't you? My guess is that a lot of people who I know who you are because you're the co-author of the leading AI textbook. So anybody who studied AI has like kind of lived with your words and read your voice and experienced your perspective.
Since the 90s.
Yeah. So how did that?
Since 95.
Yeah.
So how did that come about, and what is the I don't know, the repercussions of it having happened?
It came about, I think, mainly because the field was changing, and so I was on faculty at Berkeley, and we would go out to lunch with the other professors. people Stuart Russell, Chandra Malik, Michael Jordan, and so on. And we'd say, oh, none of the existing AI books are really up to date. That, they're all fine in their time, but the field is shifting sort of away from expert systems, more towards machine learning, away from logic towards probability. And it just felt like the books needed an update. And we said, yeah, we should do that. We should write a book. And then we never did. And then I sort of got this feeling, back then we didn't quite have the word big data, but I felt like that's what I wanted to do. And I was looking at the types of grants and support you could get as a young faculty member and saying that's not very much. And the kind of resources you could get in the company and saying that seems like a lot more. and so I headed off to industry. And then like a year later, I was at a conference and saw Stuart Russell and said, you guys probably halfway through that book we were talking about, right? And he said, nah, we keep talking about it and keep not doing it. So I said, well, let's do it. Even though we're in different places and remote, let's do it. And so we did.
So was that Sun Microsystems at that point, or what?
Yeah. Uh-huh. Yeah, I was at Sun. So I was at Berkeley and I got a job with Sun. Ironically, in the Boston office, not in California, because the Boston office was where what they were calling then intelligent information retrieval and what we would call now search, with Bill Woods running out of the Boston office. And so that's what I wanted to do. And that's where I ended up.
Right. Oh, that is super cool. I mean, but Peter, we haven't met before, but I've been a big fan for decades and decades. So this is super exciting. So again, thank you so much for joining us today. And
I would agree with Mike. That's what a lot of people know me for. And
but from my point of view, looking at your CV, go ahead. I was just going to say, looking, yeah.
Somebody was saying the other day, "Oh, you're like the father of AI," and it's like, well, one, do I look that old? I think AI is older than I am, so that can't be. And secondly, it's like I'm not like the father. I'm like the umpire. So I get to call the game. And and there's the old joke that there's 3 ways the umpires can go. You call them as you see them. You call them as they are, or until I call them, they ain't. And I'm not sure exactly which one of those my role is.
A little bit of each. Yeah.
Right. Well, I mean, so if you're not the captain of AI, you're certainly the historian and the scrivener.
Yeah.
The people that write the history have a lot of power. And anyway, but from my position, it's even bigger than just the AI textbook, because I mean, like, you were at Sun, you were there for tons of these things, as well as directing bunches of it and so forth later in your career and so on. So that I mean, what I would like to, tell you what I would like to do is just jump into the deep end. I did my degree in the 90s at Carnegie Mellon. So I overlapped with Alan Newell and Herb Simon that were there and so on. And they had a great impression on me. And one question I would like to discuss with you, or just ask you, is what do you think the state is of the physical symbol system hypothesis? Which goes all the way back to the early days of AI, and the idea that, whatever intelligence is, it's on the one hand, it's a physical system, but it can be understood as manipulating symbols. And that's what intelligence is going to be. I mean, did I botch that characterization, or what do you think?
Yeah, I think that's right. And I guess it all depends on what you think a symbol is.
Well, I guess another way to ask the question is, how have we evolved as a field or a society or anything in thinking about what a symbol is?
Right. So I think in the early days of AI and in the early days of logic, going back to Aristotle and then to Leibniz and so on, there was this idea that you could define symbols that had a close relation to the world. And I think it was Leibniz who said, let's invent this calculus for logic, and then
Let
when
us
there's
compute.
a debate, we'll just figure out the right answer. We won't have endless debates on TV. There will be a correct answer. And I think nobody really believes that anymore, right? And the reason is not because we don't have the right computation, but because nobody can agree on the definition of what does, freedom or justice or fairness. How do we define those? So, we could have a rule that says fairness is good, and if not fairness, then bad. But if we can't define fairness, then then you can't really do anything with these logical systems, right? And so, more recently with these neural net systems, we said, well, we're going to break these symbols down, right? So the big advance in language models started when we said, we already had statistical language processing, which was mostly based on counting up how many words or phrases of words there were. And sometimes you do a little bit of processing of the words with their suffixes and affixes and so on. But it's mostly just counting words, treating them as symbols. And we got a good advance when we said, well, that's not good enough, because then we never get any generalization, right? You don't learn properties of adjectives because you have no concept of adjective. You have to learn the same thing over and over again for every adjective. And you don't learn properties of color names. You don't know that there's any relation between blue and green and so on. So we said, well, let's put that back in, and we'll replace words by word vectors in this latent space. And now, to some extent, I guess they're still symbols. They're like a vector of symbols, but to another extent, they look very different than symbols. They have this fuzzier type of relationship, and it's no longer if A then B. It's more like, well, A is pretty close to B, so it should probably do pretty similar things.
Yeah. I mean, certainly one thing that comes to my mind when thinking about symbols and all is that to me, the essential thing about a symbol is it has some kind of pointer nature. It somehow refers to something else. It somehow describes or characterizes something else. And that something elseness is an important part of what it means being a symbol, so that you could have a word which is just arbitrary buzz, 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 and yet it refers to a cow in a meadow or whatever it is.
Right.
And when we shift to this neural net where it's all just a bunch of weights that have these little teeny features like black spot and goes moo, or I don't even know, whatever those features are, the figuring out how that means to point at something is sort of an additional architectural step that has to be put on, so how you get from a word vector to, okay, well, that means something else. It seems like that most neural network stuff to me seems like if you look at figure 1 of the paper, it shows the connectivity of which net is going to go from here to here to here, and then we're going to do this and that. But it seems to me like in actual intelligent systems, if I try to imagine my own intelligence, it seems like it's a much more fluid thing. There isn't a fixed figure 1 like that. And I just, I just say, where can we find the symbols within this thing? And are we ever going to see them except in the resulting behavior? And I mean, there are folks that I see on Twitter, Michael was talking about that, that are arguing that deep learning is missing symbols, and that it's climbing a tree to get to the moon because it's not taking symbols seriously enough. But I sort of feel like the old style symbols, like words and stuff like that, they're a little bit too literal, and we're going to have to find them inside the networks rather than build them in up front. Does that make any sense?
I'm more happy with the representation we have with vectors than with individual symbols, right? Because I think if you're doing mathematics and you're trying to define triangle, then yes, I can define that in terms of symbols. But if we're trying to define something in the real world, I don't think I can do that. So I'm happy with those. I think we do have some degree of connection in both directions. So we can build these vector models from a corpus of words. We have this program Word2Vec and similar programs that do that. Then going back in the other direction, it's a little bit harder to understand what's going on. But you can ask questions of these systems and they give answers, and you can, by having that kind of dialogue, you can try to understand what their internal symbols mean. And that's no different than the way I talk to a person.
The way people are. Yeah.
I don't know what's going on in your head, but we're able to have a conversation because we have ways of communicating that we agree on. So that part doesn't bother me. I guess what I think is missing is there are certain things we can do with these logical systems. We can, follow these rules and say, this is correct or this is wrong, and logical reasoning is all based on assumptions. And so it's like, if you accept the following assumptions and premises, then we can conclude such and such. And I think the current round of neural nets don't really have that kind of logic, right? They come up with an answer, but they don't really have that justification in terms of those steps of, if you accept these premises, then this follows. But I think the way to do that is just to teach them how to do that. Learn that on top of the current architecture.
Right.
We have critics. There's a lot of people out there, and a lot of people I respect and have good ideas. So Gary Marcus would be a good example of that, as somebody who's thought very deeply. And he's saying, well, here's all these problems with the neural nets, and here's all these things that they do wrong. And I totally agree with that. We got to fix those. But I don't know the way to fix that is to throw them out and go back to good old fashioned AI, right? Right. So I tried that for a decade and I gave up on it because it doesn't work. And, so it's not because there's this mystic lost art that we should go back to. We gave it up because we tried and it didn't work. And now we have something better. And the thing we have better isn't perfect yet and isn't 100% better on all dimensions, but it's a lot better in some dimensions, and it's mostly as good in the other ones. So I think we're on the right track, but we still got a long way to go.
I certainly, so for me, as an example in speech recognition, the idea that we should use our human intellect to do syllabification and word boundaries and all that stuff, and then feed it into whatever the network is that's trying to do recognition. And that turned out to be strictly worse than just feeding in the audio signal directly and giving up on syllabification. Don't do any of that at all. Just have more layers in the deep learning network. And then subsequently, researchers found, I gather, that you could see things that look like syllables in the hidden layers of the network, in the behavior. But the network had to figure it out itself rather than us saying, boom, this is a word, this is the end, trust it 100% and just use it, because it'll trade off all these other things where two words tend to always go together, and it'll tend to sort of merge that into one syllable or whatever it happens to be. And that would be the pattern that's going to happen in general, that it's going to be kind of emergent symbols rather than this big hammer Lisp code that says car and coulder, if and then, that sort of thing.
I think that's right. I think, we have, I've heard it described as physics envy, that we want all our theories to be nice and simple, like F equals ma or E equals mc squared, but they aren't. And our theories end up being these models with a billion parameters, and and that feels less satisfying.
Very much less satisfying.
I don't.
Okay, so
but
I disagree completely. I am
But
I have
it-
anti-physics envy. I have postmodern culture envy or something like that,
Yeah.
where I'm not looking for a simple equation. I'm not looking for a super powerful abstraction. I'm suspicious of super powerful abstraction. I'm suspicious of P log P or whatever it happens to be, and so forth. Even though I grant it does at least give people sort of a bit of common language to talk about a choice of architectures or a family of architectures like that. Yeah. Anyway.
And I did see an intriguing book recently that basically says even physicists have physics envy.
It's theory envy. It's math envy is really the thing.
Yeah.
Well, okay, so can I jump off on that for a second? Because Peter, you were a co-author of a paper in 2009 that just really, like, the title really resonated with me. It was The Unreasonable Effectiveness of Data, because it's a play on an older paper about the unreasonable effectiveness of mathematics, right? And so you kind of did exactly this trick of saying, yeah, mathematics is what it is, but but data is actually giving you something very deep, very powerful, very important. Can you tell us a little bit about that paper? And in particular, I think when I read the paper, it didn't quite match up with the title or what I was expecting based on the title. And I don't know if that was intentional or what, but I don't know. I've always been very moved by the unreasonable effectiveness of mathematics in the physical sciences, because it's almost cosmic, right? It's this sort of idea that I think it's wrong in a lot of ways, but I think it's an interesting philosophy, which says that there's something about mathematics that is so right that will sometimes make predictions about the universe using this mathematics, that the universe, for no reason that we can completely understand, adheres to the mathematical formulation that we've made. And but there's limits to that, and I think that dealing with intelligence, dealing with human culture and so forth, is not going to follow that kind of nice, clean mathematical description. And so what do we have instead? Well, maybe data is the thing that will give us the leverage on these kind of more human interactions.
Yeah. So I guess that, so the paper goes back to some ideas that I had been thinking about. I think the first paper that I saw that struck home for me was by Banco and Brill. And they were looking at this task of word sense disambiguation. And, it's a task that computational linguists have looked at for a long time. And I'm not sure how much of this was in their original paper versus how much is my takeaway. But it seemed like, if you want to get a paper published, what you have to do is say, well, I've got a new algorithm, and on a standard test set, I get a higher percentage. And everybody was arguing about that, and new algorithms were coming out. And you had this graph of, your algorithm going up and to the right as you get more training data. And what Banco and Brill said— happy graphs, right. What Banco and Brill says, here's, my line slightly above these other guys' line. But they said, but if we just increase the training data by another order of magnitude, then all those differences go away. And don't waste your time trying to be clever about coming up with
the algorithm, because it's about the data.
Just gather more data.
Well, you can make really fine distinctions. You can split hairs on the algorithms, but the fact of the matter is, like, good data versus bad data just washes out those differences. It's so much of a bigger difference if you have a little 2x2 design, like good data, good algorithm, bad algorithm. All the action is happening between bad data and good data. It's tiny little motion between bad algorithm and a good algorithm. Right.
Yeah. So that's the point we were trying to make in that paper.
I see. Okay. Well, that stuck with me.
And in terms of fitting the universe, I think my answer to that is mathematics is a human invention, and we decided to explore the parts of it that did fit the universe and not the parts that didn't. And so that's why I think mathematics is effective.
Well, and I think also the universe is the experienced universe is fantastically redundant. if we were actually just seeing HBO static all day long as we looked out into the world, then there would not be unreasonable effectiveness of mathematics because nothing would be predictable. But in fact, we're seeing something which in large part is this extremely low order representation of a very high order representation of a lower order dynamical process. And that means we can extract leverage using math or just using language. It doesn't have to be math. It just has to be anything that says we should view this data, this input in this way. We should make a cut here and say yes, no. And if we do that, we will get a great simplification and great prediction. And math is just the limit of that. Right. Just saying, this is the way to slice things up. And the fact that it works so well is because the universe is so degenerate. We have, we have isotropy in space and time. You can drop the apple here, you can drop the apple there, you can drop it on Newton, you can drop it in the future, and it's going to act the same in all those cases. That's the level of redundancy that's powering the mathematics, it seems to me, to make it work.
Yeah.
Well, so just to connect these two stories together, then what I'm hearing is that maybe like just the way that the unreasonable effectiveness of data, like good data is better than bad data and algorithms are less important, like getting the right symbols, like breaking the universe up into these pieces, maybe the good math versus the bad math is much less important than dividing up the universe in the right way. Once you've done that, a lot of things are going to tell you a good story.
Certainly, if we think about math in limited sense of, sort of arithmetic and F equals MA or something like that, then for sure, the hard part has to have been done before you can even start doing that kind of math. But if we take math in a more generalized sense, where it can be if-then rules and conditions and probability weightings and scoring functions, I want to say that's all math, as long as we can write it down in code somehow and implement it in a machine somehow, then we're there, like that. Then it's math either way, right? But
you're anti-math, and it sounds like you're talking about code, and I know you're pro-code.
I am pro-code. For me, the thing is, we spent hundreds of years, thousands of years developing mathematics solely to run on humans. We developed the language of mathematics, the structure of mathematics, the assumptions of mathematics, the abstract zero-dimensional point, the abstract one-dimensional line, and so forth. For that language, F equals MA, that's 4 symbols, F equals MA, to run on people. Like that. And that biases the nature of the mathematics that we created for thousands of years. And it wasn't until we built computers, mechanical computers, that there was now a second implementation someplace else that we could run code. Not just on human machinery anymore. And that created a whole vector change of different design criteria. And we started coming up with what we now think of as code. So to me, that was where the split happened. It was from code designed to run on people versus code designed to be run on jacquard looms or whatever it happens to be.
Yeah, I certainly resonate with that distinction, and and I think of myself as a code person,
right.
So I'm okay at doing math, but I know lots of people that are 10 times better than me at doing math, and I struggle with that. But if you can explain it in terms of code, then I get it.
Right. Yeah. And it's funny because, there's an instinct. My instinct is to give like a variable name versus a Greek letter. And to me, that's sort of the poster child of language designed for running on humans versus language designed for running on manufactured systems like that. And I always want to give a variable name. I do not want a Greek letter.
So I had a fun experiment once. I was talking with Percy Diaconis, a mathematician, and Susan Holmes, a statistician. Yes, and we were talking about some of this distinction of the different ways of looking at problems, and having a fun time talking about the theory of it. And I said, well, let's do a real experiment. Here's this problem that somebody gave me. Let's all go home and solve it, and then we'll meet up again. And sure to stereotype, Percy came back with his yellow-lined notes scribbled in pencils, and he'd come up with a really great solution that understood the problem. And Susan had done a R notebook in which she simulated 10 individuals for 100 time steps. And then I had done a very similar Python notebook in which I simulated 10,000 individuals for 10,000 time steps. And so it seems like, you each have your comfort zone of the types of things you do. And in the end, we all solved the problem pretty well. So, none of those methods is better than the other, but it is telling that, you use the tools that you're used to.
I think that's a great example. And, and again, up until the 1900s or something, there was really little choice but to do Percy's approach. Because if you were going to do math, it had to run on people. But now more and more and more and more, we have these manufactured technologies that we can run math on. And
so another thing that really struck me is I was working through, I was making a sort of pedagogical Python notebook for how to understand basics of probability theory. And there's like all these earn problems and things like that. And, and basically I said, well, you can just enumerate them. It's just counting. And here's how you solve some problems by counting. And then I said, well, in this text I'm going through, they do some examples by counting. And then they do this completely different approach called Bayes' rule, where instead of counting, you're using, 4 or 5 lines of algebra to solve this problem. And I said, well, wait a minute, I don't have to do that different. I can just do that by counting also. Mm-hmm. And I think the reason why we had Bayes' rules for problems like this was, it's only like 5 lines of algebra that you have to get exactly right, or else you're going to screw up. But if you didn't do that, you would have had to count like thousands or tens of thousands of instances.
Right.
Whereas I said, it's only 10,000 instances.
Yeah. Exactly.
If I could avoid 5 lines of math with only, running those in a fraction of a second, what a great trade-off.
Yeah, so man after my own heart. Absolutely.
This is just the same type of problem. It's not a different type of Bayes rule problem. It's just another instance of counting.
Yeah, and I feel exactly the same way. If I can see how to implement it so that then I just need to let something turn the crank for a second or a day, then that's the way to go. And I will get more juice out of it by implementing it than trying to figure out how to solve the recurrence and and do mathematics or do traditional analysis, put it that way, on whatever the problem is.
Right. But I got to say, if you really try to get things done, it's good to have people with different points of view, right? So I have this point of view, and this is how I solve problems. But I always enjoy having other people, people that are very sophisticated at math. I remember once we had a reading group and some paper in machine learning, and somebody was presenting the paper and said, and then here's this theorem, but I don't really understand why it's true. And we had a physicist in the group, and he got up and said, oh, well, that's because you dumb computer scientists don't know the right notation for matrices. He says, in physics, we have this special notation. And then if you use that notation, then in order to prove this theorem, it's just this cancels with that. And you're done in one step. So having that viewpoint where the whole problem is solved by notation rather than by lemmas was really useful.
Sure. Well, and even just to understand that this particular problem, whatever it was so much in the center of the wheelhouse of the mathematical physics approach that it came down to mere notation is itself an interesting fact about whatever the particular problem is like that. So, for sure. So I still think that I don't even know if anyone ever talks about it anymore, but I still think about the neats versus the scruffies, the approaches to AI that are more formally oriented, the neats versus the more, let's just implement something and see how it behaves, the scruffies. It sort of looks to me like the revenge of the neural nets in the last, 15 years is the revenge of the scruffies. How does it look to you?
I think that's right.
Though it's
although
interesting because a lot of the people doing the neural nets do it in a neat way, like not neat in the sense of like, wow, that's neat, but neat in the sense that there's
Prove
really,
theorems.
really dense math. Well, it's that the thing is that they don't, a lot of them don't prove theorems. They just manipulate equations. They start
Yeah.
off like, let's describe it this way, and now let's crank these equations a little bit, and now we have different equations, which always I found somewhat unsatisfying because like, what were wrong with the first equation? But
Yeah.
yeah, sorry.
So I think that's right. I think there's a lot of mathematical sophistication in describing what's going on, describing what the algorithms are, trying to show that the implementation matches that, trying to show some of the properties of the algorithm. But when it comes to, can this particular neural net architecture learn to solve this problem? I think that's all empirical. I don't think anybody's has good answers ahead of time of, theoretically, is this going to work or not? I guess the thing I see that's different, and this is going back, many, many years to the start of my career, which was, taking computer science from Andy Van Dam. And back in those days, if you talked about library functions, you had sort and square root, and that was pretty much it. And everything else you wrote from scratch. And so there was this idea you had to understand every bit of the code that you were producing. But now it's more like, well, I downloaded this package and these 3 other packages, and then I wrote some glue code, put them together. And, I know for this package, I know how to make one call. I don't understand anything else, what it does, but it seems to work. And Hal Abelson says we've made programming. It started off as a mathematical science, and now it's a natural science, where we're making observations of these creatures in the wild that are these software packages, and we have a field guide, which is the manual, but the field guide's often wrong. So then you have to make other guesses about how they really behave.
Right.
Then you do experiments to see if those guesses are right.
I hypothesize this is computing F equals MA. That's what I want it to compute, but I really don't know. I just got this Lindblast library. Who knows what it's doing? But it's the same old thing like with P equals NP. I can't prove one or the other, but neither can anybody else. So I use the same library that a zillion other people using. I don't know if it's correct, but they're all using it too. So we sink or swim together like that.
But I got to admit, I find it hard to work in that style. That when I download a package, I want to spend a couple hours reading the manual. And by the time I'm ready to get started, my colleagues have already finished because they didn't bother reading the manual. They just said, well, it worked. I'm done.
Right. It seems to work. Ship.
So does this have implications for how we should be understanding computer science, how we should be teaching computer science, how we should be evaluating contributions in computer science? Like, I feel like I have that maybe what I'm hearing, though maybe you guys should say if you actually feel this or not, is that like, that's not good. Like there are issues. Well, it's good and bad, but let's say it's bad in that it's not fun anymore. It's not interesting. What drew me to computer science was not slapping things together and making it do something. It was understanding all the causal connections that all together made this thing happen. And so that could mean, okay, now I'm too old and I should just like hide, let people do whatever it is that they do, or we should be pushing back and saying, okay, well, there's downsides to this new way of doing things, and we need to be careful. We need to be, I don't know. So where do you guys land on this? Are we sad about this, or are we happy about this? It's all
I think we should be happy that people could do more things quickly, and there'll be more innovation. There'll be more useful stuff created. It'll open the field up more to people who don't get frustrated quickly. So it's good that you can produce more in a given amount of time. I think we should be more careful, and I do see that happening in the last few years. That there's a lot of emphasis on fairness, on safety, and all these other issues that in the past didn't seem to be as important now, and now those are important to everyone. And this style of slapping components together probably hasn't caught up completely to that style of let's be careful about all these external issues. And maybe we have to do a better job of designing systems so that they work like that. Another thing I think is really interesting is we're starting to see this ability to do automated code completion. And that's built on taking all the examples of all the code in GitHub or whatever and saying what tokens come next. And I think that's useful. It's dangerous to a degree if you're just always accepting that without looking carefully to see if the suggestion is wrong. But I think it'd be interesting to say, we designed programming languages and programming package APIs for a human to use by themselves. And then probably they evolved a little bit when we said, well, now you're going to use them as part of an IDE that's going to be giving you completions of the method names. But now maybe we need to redesign them again. If we say we're no longer designing just for a human programmer, we're designing for a human computer team as a programmer. Maybe the things that it learns should be different. Maybe we can build in some more safety that way. And have the suggestions that come out be somehow certified in terms of safety.
Yeah, that would be great. I mean, I think about how, everything that we do to make programming easier by building virtual machines in every possible way, from higher level languages to spreadsheets that allow you to configure them and so forth, also makes the task of a machine doing search to create programs easier too, because now it can target the same virtual machine that our students are targeting, which is much simpler than assembly code or whatever it happens to be. I worry a lot that this is all being built on top of CPU and RAM and hardware determinism, which is so unbelievably fragile that if you don't get everything perfect, if you lose control of the pointer once, the machine is now no longer yours. And that unless we can think of some way to robust up that underneath us, then we're going to be, we can make all the APIs better we want until the cows come home, and we're still going to be in a disastrous situation as far as computer security. But Michael, I have to call you out for the absolute height of hypocrisy here, I think. You're saying you really like to fit in the pieces and make it all go. And yet, in fact, the way you program is using grad students, which are so completely non-deterministic and so completely opaque. How do you justify your previous statement, Michael?
Because I program in grad students for the sake of the grad students.
I see. Not to actually get the answers that you wanted.
Correct.
So I guess that's a step one in how to program in grad student is take what you get.
Right, don't be, no, as you say, it is somewhat non-deterministic at many, many levels, right? So the thing that I observe over and over again is that the students reinterpret the question. Like they actually end up answering a question that wasn't the question that I came to them with. And so it sort of doesn't matter what happens underneath of that. It's not going to answer my question, because even if they did it perfectly, they did it with respect to their understanding of the question and not mine. So I've kind of over the years, now I spend more and more time at that level, just to sort of like, okay, well, what do we think is going to be interesting to study here? Because if I can get them sort of on board with this is a really interesting question, or formulate the question in a way that's interesting, even if it's not my question, then I don't care sort of what happens the rest of it. It's like we've accomplished something useful.
Right, because what we really want is give me good stuff. And here's a guess about where good stuff might be. I can't promise anything. If you find better stuff, follow the better stuff, and then just come back and tell me about it next week, something like that. Well, so Peter, thank you so much for talking to us. I'm supposed to stop because we're using up our time, but I can't resist asking you, how do you feel? I mean, are humans all going to get wiped out? How do we need to be afraid of AI and it's going to outthink us and all that stuff, or is it going to be all right?
Uh, I think it's going to be all right. I'm not worried about Terminator-like scenarios or paperclip-like scenarios.
Maximizers.
But I am worried about, let's say, like automobile-like scenarios, right? So, automobiles are machines that conquered half the earth, and if you look at our cities, look at how much we devoted to them, look at the problems they're causing with pollution and climate change, and it really would have been good if 100 years ago, Mr. Benz or Mr. Ford or somebody said, hey, look, we got this fantastic technology that's going to do a lot of good stuff, but maybe we should be really careful about some of the bad side effects as well. And I see we're starting to do that in AI, but we really got to take that seriously. So AI is not going to murder us all as murder bots, but it is, any powerful technology can have unintended side effects, and we better be very careful about that.
Oh, that sounds right to me. I mean, that seems like the challenge is, if Henry Ford can make a buck by selling a Model T, then it's hard to say we should be doing something different. And that'll be true for every technology that comes down the pipe. But I think something you mentioned earlier, that people are thinking about the issues and focusing on it and calling it out now, certainly I think helps. There's we got to watch it the whole way, but it's better than just ignoring it and saying, "Wow, cool, new thing, shiny, just go for it." Like that. And I think, I think you're right. I think it's going to be all right. It's going to take a lot longer, and we're going to change as the world changes with us. We're going to change as our technology changes with us. And we shall see, but it's, I guess I feel like, but mostly I think we're kind of still pretty much at the beginning stages of AI. For all the amazing stuff that we get out of big data, as you say, we still have an awful lot of architectural stuff that we just really don't understand at all. There's going to be big plateaus and big breakthroughs going forward. We're just going to have to find them.
Yeah. We got our work cut out.
Yeah, that's absolutely true.
Before we completely stop though, so Peter, so what we kind of tracked your career through a certain stage. We didn't even mention NASA, I don't think, but that to me was always a really exciting one, because rocket science. But then you were in Google. You were running the research piece of Google for a while. Is that right?
Yeah. So I started out. I was actually hired into Google my title was Director of Machine Learning, and I was trying to convince them that someday machine learning might be kind of important to this company. And I think I undersold.
That worked.
Yeah. Wasn't there a big announcement? Google is a machine learning company, so you basically you took over the whole company.
Right. And so soon after getting there, I realized that there shouldn't be a separate machine learning piece that should be spread throughout the company. And a lot of the key people had just moved over to work on ads. And so there was an opening to say, well, somebody's got to run the search group. So I ended up doing that for about 5 years. Then when it got sort of too big for what I felt my skills as a manager or a leader were appropriate for, then I moved over and did the research group. And for a while I ran the whole research group. And then over time, increasingly smaller and smaller proportion of it as the company grew and assimilated other companies and spawned off whole new research groups such as DeepMind and so on that were separate. And then for the last few years, I've been sort of moved back into individual contributor role. and this year I'm actually I still have my Google badge, but I'm spending most of my time over at Stanford and at the Human-Centered AI Institute, and looking at ways of using AI for education, something that Sebastian Thrun and I looked at a decade ago, and it seems like now it's a good time to look at it again.
Oh, that's great.
Well said. So
well,
you basically took the longest possible commute from Berkeley to Stanford, is what you're saying.
Yeah. And I mentioned going to Brown as an undergrad. I'd actually lived my whole life in New England up till the time it came for grad school, and I said, well, maybe it's time to do something different. and I had heard that both Stanford and Berkeley had pretty good computer science departments. So I said, well, let's change my life. Let's move out to California. So I applied to both, and both schools unanimously agreed that I should go to Berkeley.
And the rest is history. Well, Peter, I mean, you certainly pass for a California type at this point, I think.
Yeah.
And thanks so much for being willing to talk to us today. This was really great. And
yeah, it's a pleasure.
So much thank you. And I'm looking forward to see what you'll be doing going forward.
Okay. Yeah. Thanks a lot.
This was Computing Up. Thanks for listening.